Hello class. In lesson 2.7, composition of functions, you're going to evaluate the composition of functions with multiple representations. We'll start by first reviewing how to evaluate a function. So consider that f of x equal to 2x minus 3. In order to evaluate the function at 5, f of 5, what this notation means is that we're going to simply replace the value of x with the number 5. So 2 times x is now 2 times 5 minus 3. And well, that simplifies to 10 minus 3, which is equal to a total of 7. So f of 5 equals to 7. Now, in reviewing this, I also want to discuss again what this means. What this means is that when x is equal to 5, your y value is equal to 7. Now, in terms of a graph, if I have my x-axis, my y-axis, f of 5 equals to 7, I don't know why I'm writing it again, f of 5 equals 7 means that when x is equal to 5, the y value is going to equal to 7. So this is going to be a point on the graph. If I do and evaluate this function f at multiple places, I can identify more points, and then connecting those points with whatever curve, again, I can see what the graph is going to look like. So this is, again, just simply identifying that I have the coordinate 5, 7 on the graph. Now let's evaluate it not at a number, at a letter. So if I want to find f of c, again, what this notation means is that we're going to replace the value of x with c. So instead of 2 times x minus 3, it's going to be 2 times c minus 3. And well, of course, this can't be simplified any further. This is all we end up having, just that. Now let's look at example B. So we want to now evaluate f of 4a. Well, again, f of x, let me just write it here, f of x equals 2x minus 3. So f of 4a means that we're going to replace the value of x with 4a. So this would be 2 times 4a minus 3, which simplifies to 8a minus 3. So f of 4a equals to that, which again, if I had a graph that had an x and y value and we had coordinates in terms of a and so on, we would have this coordinate. We would have coordinate 4a, and the y coordinate would be 8a minus 3. So that would be the coordinate to this point. Now let's look at this example. I've had these labeled wrong. This should be D. So let's look at example D. So in example D, again, f of x equals 2x minus 3. And we want to now evaluate f of 5x minus 1. Well, to evaluate f of x minus 1, this again means that we're going to simply replace our x values with 5x minus 1. So instead of 2x minus 3, since we're going to have f of 5x minus 1, it's going to be 2 times f of 5x minus 1 minus 3. And well, to simplify this, this requires, again, us to distribute this. So we're going to end up with 10x minus 2 minus 3, which can simplify to 5x minus 5. So f of 5x minus 1 equals to 10x minus 3. Now, sometimes in mathematics, we have to plug a value of x into a function and then use the output to plug it into another function. So for example, let's say you're going to shop for Mr. Aviles because you want to buy him a gift for Teacher Appreciation Week. Now, you have a coupon for a 5% off of all items, and the store is taking a $10 off purchases at the register. So let's say that you really appreciate all the work that Mr. Aviles is doing, and you buy him a gift that costs $29, okay, before discounts. Let's find the price of the item with the 2 discounts. And the price of the item, or finding the price of this item, again, is going to be an example of a composition function because of the following. So we have that the price of this item is $29. So first of all, we're going to use the first discount, which is a 5% off coupon. So out of 100% of the price, you're going to take 5% off of it. So the $29 item that you're going to purchase is now going to cost 95% of its original cost, which is 0.95 in decimal format. Now, to identify and determine what the price of that is, we're going to simply now multiply 29 with 95% or 0.95, I'm sorry, 95%, 0.95. And that's going to bring the cost to $27.55. Now, since when you take this item now that now costs $27.55 and you took it to the register is going to take again $10 off. So $27.55 minus the $10 off at the register, that's going to bring the total item to $17.55. Now, this is an example of a mathematical concept referred to as composition functions, where I get again one function, get that answer, and then that answer goes into another function. I do a second step with that. This is referred to as composition functions. So for example, if I write this as a rule, I'll say C for coupon, C of D for dollars, is that I'm going to end up getting the dollar amount of the item and multiplying it with 95%, so 0.95, because that's going to, again, the 5% discount means, again, like I did over here, that's 100% minus 5%, which is 95%. So I'm only going to pay whatever the dollar amount is going to be multiplied with 95%. Well, then this item, again, this amount here, is then going to be applied again to a different discount at the register. So I'll call it R for the register. R of D also, because we're talking dollar amounts. That's going to get the dollar amount and subtract a flat $10 fee. Okay, so in the terms of composition, this value here will become the new value of D. So this is now going to be R of D times 0.95 or 0.95D. Let me write like that, which would mean we have 0.95D minus 10. So this equation here would be the equation that can tell me again the price of the item when both discounts are applied. And this is again is referred to as a composition function. So let's say again, and the notation for this would be this. We say we're evaluating R of C when the dollar amount of the item is $29. So if I plug in 29 here, and for the letter D, 0.95 times 29, and then minus 10, that equals to a total of $17.55. You see this amount right there. So this is an example of a composition function. So let's go to the next page and let's talk about this in more detail, okay? So let's talk about what a composition function is and what the notation is. The composition of the function f with the function g is defined by this notation. Let me do it in black. F of g of x, which is denoted in this term right here. So it's defined as this. So this notation, as you'll hear me call it fog, fog is referring to taking a function g and using that function as the input values to this outside function f. And like the way that we read this is we say the way that we read both notations is f of g of x. That's how we read this notation and this notation. Now, what we're going to focus on today is learning how to evaluate these functions at specific numerical values, okay? So the steps in evaluating a composition function starts again through the inside. So we start with evaluating and seeing what number this is going to be right here, and we evaluate the inside part first. So we would evaluate g of x first. And then using the answer from g of x, we're then going to substitute it into f of x. And that's how we evaluate the composition of a function. So for example, let's say f is equal to 3x minus 5 and g is 2x plus 1. We want to evaluate the function f of g of 3. Well, to evaluate this, what we're going to do is that we're going to start in with the inside first. So the first thing we're going to do is evaluate g of 3 and figure out what g of 3 equals. Well, g of 3 is going to equal to 2 times x, which is now the value of 3, plus 1. So g of 3 is going to end up equaling, this is 6, and 6 plus 1 is 7. So g of 3 is equal to 7. So now that we know that g of 3 is equal to 7, we're now going to evaluate f at that value 7. So we're going to get this answer of 7 and plug it into the function of f and figure out what the y value is when x is equal to 7. Well, again, our function here for f is 3x minus 5. So f of 7 would be 3 times 7 minus 5, which is 21 minus 5, which is a total of 16. So what is the answer to this? Well, the answer to this is 16. So f of g of 3 equals to 16. That is our answer. Now let's look at this next example, example B. So first of all, this notation is the same thing as the previous one. This g, we read this as g of f of 3, which can be written as g of f of 3. So we're going to first start with the inside and first figure out what f of 3 equals. Well, again, using the same definition as above, f being 3x minus 5, f of 3 would be 3 times 3 minus 5, which is going to end up equaling to a total of 4. So f of 3 is equal to 4. And since we know that f of 3 is equal to 4, we're now going to evaluate g of 4. Sorry, let me move this over here to the side. So what we're going to do now is get this value, this output value, and evaluate g when x is equal to 4. Well, since the function of g is still 2x minus 2x plus 1, this would be 2 times 4 plus 1, which is a total of 9. So g of 4 is equal to 9. Sorry, 9. So that means that this equals to 9. So our solution is this. And let me write it over here. G of f of 3 equals to a total of 9. Okay, let's now look at example C. So here we have f of 4. So f of 4. So again, starting on the inside, we're going to first evaluate f of 4. Which again, using the same rule as before, is 3 times x, which is now 3 times 4 minus 5. And 12 minus 5, that's equals to 7. So this here equals to the value of 7. So we're now going to evaluate the outside f with the value of 7. So we're going to get, again, f, and now substitute in the number 7 into f, which since it's the same equation, it'll be 3 times 7 this time, minus 5, which is 21 minus 5, which is 16. So f of 7 equals to 16, which means that f of 4 equals to a total of 16. So there is your solution. Now, in the previous three examples, we were finding, again, a specific y value, a specific output value for the compositions. Okay, now let's look at using the same rules for f and g. Let's now find the following expressions, which is now going to come up with an equation that can help me figure out the output value for any situation for x. So here, I want to evaluate f of g of x. Okay, so right here, we're not going to figure out one specific y value. We're going to figure out all of the y values for this composition. Well, to do this, this notation, which again is the same thing as f of g of x written like this, means that we're simply going to get the function of g and plug it into the function of f. So this right here is going to be plugged into f. So to figure out what f of g of x is, we're going to get the function of f, which is 3x minus 5, right here, as you see right here, 3x minus 5, and replace the x value with g. So this is 3 times g of x minus 5. Well, we know what g of x equals to. G of x is defined to equal, again, to a function. G of x is defined as 2x plus 1. So if I replace this with the rule for g, I get that f of g of x is equal to 3 times 2x plus 1 minus 5. So all I'm doing, in other words, in very simple layman's terms, what I'm doing to evaluate this composition and to figure out what this composition is equal to, it's simply going to get this function of f, let me highlight it here, this function of f, and plug that into the x of function f, as you see right here, as indicated right here in the bottom. So instead of 3x minus 5, I have 3 times, replacing the x with 2x plus 1 minus 5. And that is your composition. Now you can leave it like this, but I'm going to ask you to do some algebra here and to simplify this by distributing that common factor. So this will be 2x plus 3 minus 5, which simplifies to 6x minus 2. So this is our composition. F of g of x equals to 6x minus 2. Now, if I'm doing this composition in the opposite order, again, order matters. This notation, g of f of x, means that we're evaluating like this. We're doing this composition. So the f is now on the inside. So since f is on the inside is going to be plugged into the outside function. So with g of x being, again, 2x plus 1, and f of x being 3x minus 5, what g of f of x is going to equal to, it's going to equal to the result of getting this function here and plugging it into the x of the outside function. So we're going from inside out. So this, instead of 2x plus 1, it'll be 2 times, we replace the x with f, which is 3x minus 5 plus 1. And again, that's the composition. So this technically is your answer. Like I said, this technically is your answer, but I'm going to require you to do some algebra here, so you'll simplify, and you end up with 6x minus 10 plus 1, combine like terms, and you end up with 6x minus 9. Okay, let's continue practicing evaluating functions, given that we have h, k, p, and m, and we want to find k of h of 2. So k of h of 2. So again, whether it's written in this notation up here in yellow or this notation down here in blue, it means the exact same thing, that we're going to start by first figuring out what h of 2 equals. Well, since h of x is 2x minus 3, again, up here, as you see right there, that means h of 2 would be 2 times 2 minus 3, which is 1. So h of 2 is 1. We're now going to use this 1 and plug this 1 again into the value of k. So let me move this over here to the side. So we know that this part right here equals to the value of 1. So what we're going to do is now get k of x, which is x squared plus 4x plus 5, and use that as the new x value. So we're going to now evaluate k when x is equal to 1. So 1 squared plus 4 times 1 plus 5, that equals to a total of 10. So k of 1 equals 10, which means that the entire composition, k of h of 2, equals to the value of 10. So this is your answer. Let's now evaluate example B. Example B, we're going to evaluate h of m of negative 1. So h of m of negative 1 would be, this notation would be the other way of representing, again, what we have on the top. So this, again, starting with the inside, we want to first figure out what m of 1 is. Well, m, again, if you look at the top of the page, m is 3x plus 2. M of x equals 3x plus 2. So m of negative 1 means that we're going to end up with 3 times negative 1 plus 2, which this is going to be negative 3 plus 2, which is negative 1. So this value right here equals to the value of negative 1. So replacing that with negative 1, we're now going to evaluate the function h at that input of negative 1. So with h of x being the function, what is h? H was 2x minus 3. Okay, this was h. We're now going to evaluate and plug this into the x of h. So 2 times negative 1 minus 3 is going to give us a total of negative 5. So h of negative 1 is equal to negative 5. So this equals to negative 5, which means that the entire composition, h of m of negative 1 equals negative 5. So for the next example, k of p of x, which again is k of p of x. Okay, this, we're going to start with first p of x. So this notation is just asking us to get this and plug it into the outside function. So we have p of x. I'm going to put k first, I'm sorry, k of x, which is the x squared plus 4x plus 5. And now we want to do it for all values of x, not just one specific number for x, all values of x. So I'm going to set this up a little bit differently in order to do this. So I'm going to put k first, and I'm going to put p second. Well, it doesn't really matter because as long as you understand the direction. So let me do it the other way, all right? So let me start with P. So P of X is equal to the square root of 3x plus 1, and K of X equals to x squared plus 4x plus 5. Since we're not doing a specific number for x, there's no number to plug in here, and all we're going to do is get all of P, and plug it into the x of K. Now K has two values of x, so both of these x's are going to be replaced again with this value here. So this value here is going to go into this x and into that x right there. So that means that K of P of x is going to be the square root of 3x plus 1 to the second power. That's that first x right there. Sorry, I meant to get the highlighter. That's that first x right there. Plus 4 times the value of x, which again is going to be the square root of 3x plus 1, close parentheses, and then plus 5. And there is your answer. Now, you can't simplify this too much. You can't get rid of the square root and the square since they are inverse operations. And this portion right here, let me highlight it in red. This right here can reduce to the following. It will just simply reduce to 3x plus 1 because the square and the square root cancel each other out. But that's pretty much it. That's the only simplification that you can do other than, of course, combining like terms. The second part, or the second term, can't be simplified. You cannot multiply the 4 into the square root of 3x plus 1. So you can only, in order to indicate that you're multiplying without the parentheses, is to write it like this, without the parentheses. So this is the same thing as this, multiplying 4 with that, just without the parentheses, that's all. And then, of course, you have the plus 5. And other than simplifying by combining the like term of plus 1 and plus 5, there's really nothing else that you can do here. Sorry. So this would be 3x plus 4 times the square root of 3x plus 1, and then plus 6. So this is K of P of X. And that's your answer right there. Okay, let's review and let's practice one more examples of how to evaluate composition functions at a specific value for x using multiple representation. So here on the top of this last page of our notes, we have four functions, f, g, h, and this function k described in the word problem right here. So we have f up here. This table is for function g. Here we have function h, which is a piecewise function. And over here, we have the function k, which is a description. So let's start with writing the equation for k. So k of x is a quadratic function. That means k of x equals to x to the second power, okay? That's what quadratic means, x to the second power. Now it's going to have a horizontal translation of 2 units, followed by a vertical translation of -3. So a vertical translation of +2 and -3. So the equation for k of x is going to be the following. So x minus 2, in order to move it to the right, because it's +2, so we want to move it to the right, that's going to be -2 to the second power. And a vertical translation of -3, so we want to move it down 3, so -3. So this is what k equals. It's a quadratic equation that has been shifted 2 units to the right and 3 units down. Okay, so now that we have that, let's look at example A. Let's evaluate f of g of 3. Okay, well, we have to start by first evaluating g of 3. So we're going to work on the inside and first figure out what g of 3 is. Okay, well, if I look at the equations up here, or look at the functions, I'm sorry, g is defined by this table. So to use the table to evaluate g of 3 right here, I'm going to look for where the value of x is 3, okay, and see what the value of y is. Well, notice that there is no value of x over here. I do not know what the value of g is when x is equal to 3 because it is not given to me. And since it's not given to me, then it is unable to determine what this value is going to be. So this is undeterminable. So I cannot determine what that value is going to be. So let's move on to the second example. So for example, h of f of 8 means we're going to evaluate h when f of 8 for the y value of f of 8. So starting with the inside, we first have to evaluate f of 8 first. Now f, the representation of f is this graph right here on the left, this one right there. So it's not like I just plug it in. What I have to do is look at the graph and see what the y value is when x is equal to 8. So obviously this is my x-axis. Here's my y-axis. And f of 8 means to look at the x-axis, so right here at 8, and determine what the y value is. Well, if I look at the graph, the y value when x is equal to 8 is negative 1. So here, when x is equal to 8, the y value is negative 1. So that means that f of 8 equals to negative 1. So since we now know that this is equal to negative 1, I can now evaluate h. I can evaluate h of x when x is going to be negative 1. So I now need to figure out what h of negative 1 is going to equal to. So let's look up here. H is a piecewise function, and there's 3 pieces to use. We use the top piece when the number I'm plugging in is a number less than 1. H is equal to negative 4 if the value that I'm plugging in is equal to exactly positive 1. And h is equal to negative x when the number I'm plugging in for x is a number bigger than 1. Well, the number I'm plugging in into this function h is going to be negative 1. So from the piecewise function, I would use the top piece since negative 1 is a number smaller than positive 1. So I'm going to plug in into here. So here in this equation, let me erase this quick first. H of x is going to be the absolute value of negative 7 plus 3x. That's the only piece, and let me zoom in, that's the only piece that I have to worry about. So of those 3 pieces right there, I only have to use the top piece since the number I'm going to use, negative 1, correlates that negative 1 is smaller than 1. So now to evaluate h when x is equal to negative 1, we're going to get the absolute value of negative 7 plus 3 times negative 1, which is 3 plus negative 3, since 3 times negative 1 is negative 3, which is the absolute value of negative 10. And the absolute value just simply makes everything positive, so we end up with positive 10. So h of negative 1 equals 10. And there is my solution to my composition. So h of f of 8 equals to the number 10. Now moving on to the next example, we now want to evaluate g of k of 0. So we'll start with the inside first and evaluate k of 0. Well, k of 0, again, well, k of x, the equation for k of x, again, since the quadratic one, remember that's x minus 2 to the second power minus 3. So we want to start by first evaluating k of 0. So that's going to replace the x with 0. 0 minus 2 is negative 2. And negative 2 to the second power is positive 4. Now, if you're going to use the calculator to evaluate this number to the second power, again, remember, you need to plug this in using parentheses, just like I've noted here. So k of 0 equals 1. So we're now that we know that this is equal to 1, we can now evaluate g when x is equal to 1. And I'm not going to write the rule for g because g doesn't have an actual equation. We don't know what the equation is. We have to rely on the table, okay? And g of 1, well, cannot be determined because, again, the only values of g that I have are these values right there. And 1 is not on the list of the x values for g. So we don't know what that is. So this is indeterminable. Now moving along to the letter D, we want to evaluate f of 2. So starting with the inside, we want to now first figure out f of 2. Well, again, f of 2 is the graph. We don't have the actual equation for that. So since we have a graph representation of the function f, we're going to have to look up here at the graph and figure out what the y value is when x is equal to 2. And this is a tricky one because look, if we look at the x values, which again right here at 2, there's 2 points that we have. Well, open points do not count. That's why they're open, because again, we have an open value right there. This y value of 4 doesn't exist when x is equal to 2. So these 2 points right there, the one that's going to count is going to only be the closed one. So when x is equal to 2, the y value is 1 on the function f. So for letter D, f of 2 equals 1. And now what we're going to do is now, since we know that this value equals to 1, we're now going to evaluate the outside function, which happens to be the same function f, now at the value of 1. So f is going to be evaluated at 1 now. So I'm going to plug in again the 1 into the x of f and see what the y value is. Now again, since we don't have the actual equation, we only have the graph representation of the equation, we're going to use the graph. So just like before, we're going to now look at when x is equal to 1 and see what the y value is. Well, the y value is 4. So when x is equal to 1, the y value is 4. So that means that f of 1 equals 4. So f of 2, that's going to give equal to a value of 4. And there's your solution. Let's now look at example E. We want to evaluate g of h of 2. So this notation, just to remind us, means this. It's equivalent to this. So we want to first start by evaluating h when the x value is going to be 2. Well, again, h is a piecewise function. And again, there's 3 pieces. Let me go back. Let me scroll up again to see what those 3 pieces are. The first piece of h, again, is the absolute value of 3x plus 3x when x that we're going to plug in is a number smaller than 1. Well, it can't be that since we're plugging in a number 2. We can't use that. We can't use the middle piece because we can only use the middle piece if the number we're going to plug in is exactly 1. So we can't do that one. So the piece we're going to use is negative x. Since the number 2 is bigger than 1, we have to use the third piece. So we have to figure out what h of 2 is, where h of x is going to equal to this piece right there. So let's write that first. Okay, so let's write that first. So we're going to write h of x is going to equal to negative x. And we want to figure out what h of 2 is, which is going to be negative 1. Remember, this negative x is the same thing as negative 1 times x. So negative 1 times the value of x, which is going to be 2, that's going to end up equaling to negative 2. So h of 2 equals negative 2. So this, highlighter, this equals to negative 2. So now we're going to evaluate the outside function, which is g, at this value of -2. So we're going to now figure out what g of -2 equals. So let's see. Well, if I look at the table G, I'm going to come across the same problem as before. It is indeterminable. The only values of x that I have for the function g are -4, -1, +2, +5, and 7. Since I do not have the x value, I do not know what the y value is when x is equal to -2, then I can't figure it out. When x is equal to -4, the value is pi. When x is equal to -1, the value is 3. When x is equal to +2, the y value is 3, and then so on, okay? So I can evaluate this. So just like the previous 3 examples above it, this is indeterminable. We do not have enough information to figure out what the y value is for the function g when x is -2. Now you might be thinking, well, can't we come up with an equation? Well, if we had an idea what the equation was, but yes, but the idea again right here is to do this without a calculator. So there's no way of doing it again without the calculator. And finally, our last example, it's a doozy. Here we want to evaluate h of f of h of k, g of f of h of k of 3. So g of f of h of k of 3. So working all the way to the inside, there we go, those are all the parentheses. Working our way from the inside, we are first going to evaluate what k of 3 equals. Well, again, first of all, k of 3, let me write this on top. K of x is again the quadratic of x minus 2 to the second power minus 3. And we're going to start by evaluating what k of 3 equals. So this will be 3 minus 2 to the second power minus 3, which is 1 to the second power minus 3, which is -2. So k of 3 equals -2. We're now going to get this answer and work again on outside and now figure out what h of this value of -2 equals. Well, again, h is a piecewise function. Let me move this down. H is a piecewise function. And of the 3 pieces we're going to use the top piece yet again because the number we're plugging in is -2, and -2 is smaller than 1. It's not bigger than 1, and it obviously doesn't equal to 1, so we're going to use this piece right there. So h of x is going to be the absolute value of -7 plus 3 times x. So this would be the absolute value of -7 plus 3 times -2. Which simplifies to -7 plus -6, which is -13, but the absolute value makes everything positive, so +13. So h of -2 is +13. So now that I've done that, I now want to plug in that answer into, work my way out, into the function f. And make it a little bit smaller and put it underneath here. And I now want to work with the function f and evaluate f when x is now equal to 13. Okay, so let's look at f. Well, if I look at f, I can determine what the y value is for f because the highest that this thing goes is 10. So since it doesn't go any higher than 10, I do not know what the y value is going to be when x is 13. So I can't continue from this on. So from this point on, I don't know what this value is, which I can then not plug it into G. So this is indeterminable. And there, that concludes our notes for topic 2.7, composition of functions. If you have any questions, please send me a message through Parent Square Remind. And like always, I appreciate you watching and I hope you have a great day. Goodbye.